This is revision for OCR Gateway Physics. We're looking at section P1C, and in this tutorial we'll cover transverse waves, the wave speed equation, reflection, refraction and diffraction, the electromagnetic spectrum and applications of transverse waves. So we'll begin by looking at transverse waves, and across the top here we've got a few examples of transverse waves. We've got a Mexican wave here, we have ripples on water, light, and all parts of the electromagnetic spectrum are all transverse waves. So we can draw a transverse wave like this, and a key feature of a transverse wave is that the particles carrying the wave vibrate or oscillate at right angles to the direction in which the wave is travelling. So in this example here, let's imagine our wave is moving from left to right. Now and let's think about our ripples on water as an example. So the ripples on water spread out from the centre there. So our wave direction here is from left to right, just as in this diagram here. Now if you were actually sitting in the water, bobbing about on the water, or if you were in a boat on the water, you wouldn't move in this direction, you would actually be bobbing up and down like this. So you would be moving up and down every time a wave came past you. Okay? So we can say that the direction of oscillation is at right angles to the direction in which the wave is travelling. So these are my oscillations here. There are some key features of a transverse wave which we're going to label. The first are the crest and the trough. The crest of the wave, as you might imagine, is the peak at the top right there, and the trough, the opposite part at the bottom. The wavelength of the wave is the distance between any two identical points on that wave. So we could draw the wavelength in there, excuse the writing. Equally, we could draw it between these two troughs down here, or we could draw it between this point, these 2 points on the wave. So if you look, we can see the wave is about to go up, and here again the amplitude is increasing, so these 2 points are identical, and hopefully we should be able to see that this length and this length are all the same, they're all equal. Wavelength is a distance, and so it's measured in meters. Another key feature of a transverse wave is the amplitude. We need to be careful when we're thinking about the amplitude. It is the height of the wave, but it's the height of the wave from this imaginary centre line here. So if I were to draw this line on, I could mark my amplitude on as the distance between that centre line and a crest, or the distance between that centre line and a trough. The frequency of a wave tells us the number of complete waves, wave cycles or oscillations per second. It's measured in hertz, or Hz for short. You only need to remember one of these terms for exam purposes, so the number of complete waves or the number of complete oscillations per second, whichever you find it easiest to remember. Now we'll illustrate frequency by thinking about these two transverse waves at the bottom here. If each wave was moving in this direction at the same speed, then as an observer standing over here, I would see more waves come past me each second from this wave than I would from this top wave. That means that this bottom wave has a higher frequency. So we can represent a higher frequency wave by showing a wave that's more squashed up. Okay? Not technical terms, but if you see a wave that looks like this, then this is of a higher frequency than this one here. We could also describe this bottom wave by saying that it has a shorter wavelength. So we can see that this distance is shorter than this distance. So the wavelength and the frequency are related, and we'll look at how in the next slide. Frequency, wavelength and wave speed are all related by this equation. So wave speed equals frequency times the wavelength. We're going to use this to solve a problem in this example here. So in our example, Dylan is standing on the end of a pier. He measures the water waves going past him. The wavelength of each wave is 1.3 meters, and he counts 2 waves every second. Find the wave speed. So to find the wave speed, we need to multiply the frequency by the wavelength. We're told that there are 2 waves going past every second. This means that the frequency is 2. The wavelength, we're told, is 1.3 meters. So working that out gives us 2.6 meters per second. If you're sitting the higher tier paper, you may also need to calculate the frequency or the wavelength. So putting that equation into our triangle, we have our 2 things multiplied together, which must go at the bottom. And that leaves us with the speed at the top. So now let's write 2 new forms of the equation. If we're calculating frequency, we cover that up, and we're left with speed divided by wavelength. And if we're calculating the wavelength, we cover that up, and we're left with speed divided by frequency. Okay, so our second example, capital FM broadcasts on a frequency of 98 megahertz. Calculate the wavelength of the radio wave. And we're told that radio waves travel at the speed of light, which is 3 times 10 to the power of 8, that should say meters per second. Okay, so we know from this we need an equation that contains frequency, wavelength, and probably wave speed. So we find that at the front of our exam paper, speed equals frequency times wavelength. We need to work out the wavelength and not the speed. So we're going to write that into our triangle. We've got frequency and wavelength at the bottom and speed at the top. We then cover up the thing we want to work out, which is the wavelength, and we're left with speed divided by frequency. Now we can substitute that in. The speed is the speed of light and radio waves, which is 3 times 10 to the 8. The frequency is 98 megahertz. Now mega means million, or times 10 to the 6. So you could either add 6 zeros after that, or you could write times 10 to the 6. Now you could put it into your calculator like this and come to an answer. I'm going to do a further step of cancellation just to simplify it. And I'm going to say that I'm going to divide the top and the bottom by 10 to the 6. So if I divide the top by 10 to the 6, I actually do 8 minus 6, which is 2. So I'm left with 3 times 10 squared. And at the bottom I've got 98. 10 to the 6 divided by 10 to the 6 is 1, so I'm just left with 98. And that's a simpler thing to put into my calculator. You don't have to take this step, so if you're not confident with the maths, please ignore it. What I do recommend that you do, if you don't know how to put these into your calculator, that you go and check with your teacher. You could, if you had to, just put in all of the zeros. So instead of writing 3 times 10 to the 8, you could write 3 with 8 zeros. And 98 times 10 to the 6 is 98 with 6 zeros. and then we cancel. So we're going to get 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and we're left with 300 divided by 98. And we should get the same answer, which is 3.1 metres. Generally, when you're giving an answer, round to 1 decimal place. Okay, moving on to reflection. So, key things to remember if you are drawing a reflection diagram is, first of all, use a ruler, which I'm not doing, sorry about that. Secondly is to make the angle of incidence equal to the angle of reflection. So I'll come on to what that means in a moment. And the third thing is to draw arrows to show the direction in which the light or the wave is travelling. So if this is my plane mirror here, that just means a flat mirror, and this is my light reflecting off of it, I could draw a line at right angles to the mirror here, an imaginary line, and this line is called the normal. Now the angle of incidence is the angle between the incident ray, which is the ray coming in, so that's my incident ray, and the normal. So we can label that I. I is my angle of incidence. And then this ray here is called the reflected ray. So we can call this angle between the normal and the reflected ray R, and that's the angle of reflection. Now you won't be expected to measure it using a protractor, but it should appear by sight as though these two angles are pretty much the same. So any type of wave, including all parts of the electromagnetic spectrum, can be reflected. Another behaviour of all waves is refraction. All waves can be refracted. This picture at the top up here shows an example of a phenomenon which is caused by refraction of light. If you look at this picture at the bottom here, you may have done something similar to this in one of your physics lessons, and this also illustrates refraction. We can see that when the light travels through the air at this point here where it meets the glass block, the light doesn't continue in the same direction, or most of the light doesn't continue in the same direction. It actually changes direction. The light changes direction again as it leaves the glass block. So rather than getting light travelling straight through and coming out this way, we end up with 2 points where the light changes direction. And this is due to refraction. Now what's actually happening is when the light travels between the air and the glass, it changes speed. The light slows down because the glass is more dense than the air surrounding it. So when the light travels from one medium which is less dense to a medium which is more dense, it slows down. When the light slows down, it changes direction. The same thing happens, or the opposite happens, as the light leaves the glass block. It goes from a substance which is more dense to a substance which is less dense, the glass to the air. The light speeds up and it again changes direction. So all waves can be reflected, all waves can be refracted, and all waves can be diffracted. Diffraction simply means waves spreading out, and we can see illustrations of waves spreading out as they pass through a gap in these 3 diagrams here. In our previous diagrams, we've shown a wave or light, namely light, by drawing a ray or a line to show the direction in which the wave is travelling. In these diagrams here, we've got a different representation of a wave. Instead of showing the direction that the wave is travelling in or drawing a ray, we've got a series of lines here, and we can think of each line as representing a wavefront. For example, it could be the series of crests of a wave or the series of troughs of a wave. So let's compare these 2 diagrams at the top of the page. In each diagram, our wave is travelling from left to right, so each wave is travelling in the same direction. And as each wave travels, it passes through a gap. And we can imagine this as water waves passing through a harbour, or something like this situation shown in this picture below. First, let's look at the wavelength of each wave. Now we can see by the distance between these lines that the wavelength of this wave on the left and this wave on the right is roughly the same. Now let's look at what happens after the wave has passed through the gap. Well, we can see that this wave on the right-hand side spreads out much more than this wave on the left-hand side. And that's to do with the size of their wavelength compared to the size of the gap through which they're passing. We can see that this wave on the right, the one that spreads out more, has a wavelength that's actually very similar to the size of the gap that the wave is passing through. The more similar in size the wavelength is to the gap, the more diffraction will occur, the more the wave will spread out. In this example on the left, we can see that the wavelength is actually much smaller than the size of the gap, so we get much less diffraction. The wave doesn't spread out anywhere near as much as in this example. In this final example at the bottom here, we still have a larger gap, similar to this example, but this time the wavelength is also much larger. And since the wavelength is similar to the gap size, we get a lot of diffraction occurring. This diagram illustrates the electromagnetic spectrum. There are many parts of the electromagnetic spectrum, but all of the parts consist of transverse waves, which we looked at in the start of this section. We have already mentioned in previous tutorials infrared, when we've looked at heat, and visible light. We will come to look at other parts of the spectrum in future tutorials: radio waves, microwaves, ultraviolet, X-rays and gamma rays. Now all of these things are transverse waves, as I've already mentioned. Another thing that they all have in common is they all travel at the same speed. They travel at the speed of light. We can see how they differ by this illustration here, this part of the diagram here. We can see that radio waves have waves which are more spread out, so a longer wavelength and a lower frequency. Whereas at this end, when we're talking about gamma rays, the waves have a very short wavelength and high frequency. Now, high frequency also corresponds to high energy, so gamma rays are high energy waves and radio waves are much lower energy. You need to be able to name the parts of the electromagnetic spectrum in order, either from long wavelength to short wavelength or the opposite way round. If you can't already name these in order, then I suggest you go onto YouTube and search for the electromagnetic spectrum song, and there's a song there that will really help you remember those in order. And that is it for P1C.